Alright everyone, thanks for coming again. And so this afternoon we're going to start looking into the new models. We plotted our network, we start measuring some metrics out of it, mostly on the topology, the large-scale structure of the network. Now we're going to set up some network new models to test if this structure they are significantly higher or lower than expected by chance. And we can use the same new models for tomorrow when we start looking at the properties, the local properties of the network, the ones based on the individual. These new models are quite general. They can be used for other research questions you may have, for example, the community structure, ecological community structure, and what else? Some of them are similar to the permutation tests we have done before. So because of these similarities, we'll start just refreshing our mind why we need a new model, and a little bit about the hypothesis testing, and then we go through some details of these, I think, 7 models that I have prepared for us. And this part will be quick, and then we have a long R script to work with, step by step, how to do it. And then I think it would be better if you guys do yourselves, and then I'll be walking around and helping out. The good news is I think we just need the vegan package for that. So if you're good with the vegan, then everybody can work. So no iGraph or anything. Maybe iGraph, but we'll see. Good, so we're gonna use a new model because our social data, in this case our network data, usually won't meet any assumption of the conventional statistical tests. So we cannot compare our empirical results with those theoretical distributions. So we have to come up with our own distribution. Network data is usually non-independent, and there's lots of autocorrelation in our data, and so probably there won't be any theoretical distribution that is feasible for us. So just to remind ourselves, our goal here is to compare our empirical results, in this case, one network metric, with new distributions generated at random, not completely random. We want to constrain some biological features of the data. The more constrained is our randomization process, more statistical power we will have to our test. Comparing with the completely random distribution would be very likely that we would reject the hypothesis, the null hypothesis. So we want this null distribution here based on our data. We're going to choose a metric this time, a network metric. Could be the modularity, for example, could be connectance, or whatever metric you want. The idea is you calculate for your empirical network, then we go back to either our raw data, the group by individual matrix, or association data, and then shuffle them according to some rules, and plot the network again, calculate that metric, and save. And did this at least 1,000 times. You have the null distribution, and then we compare our observed value metric to the null distribution and see out of 1,000 random values, the proportion of those random values that are greater or smaller than the one we observed. Again, we choose usually an alpha value of 5%, and the proportion of the random values that are different than our observed is what will give us the p-value, the famous p-value. So we can present then, for example, if we calculate for modularity, we can either present our observed one and say 32, and then we have a p-value of, I don't know, 0.1. Or more commonly, we will present this, the observed metric, and then the confidence interval. Say it goes here, 15 to 0.22, and this is your 95 confidence interval. So this is the confidence interval of our null distribution, and in this case our observed value is outside of it. So that means it's higher than expected by chance. This is your null expectation. So yes. Again, the art of building a null model. You want to generate a null benchmark distribution, randomize some features of your data, but constrain others. And choosing them it depends on the type of data you have, again, on your question and on your hypothesis. There's many ways of building null models for social network data. I organized them here. I think there's 1, 2, 3. I think it's about 7 or so. And I try to organize them more or less like this. And how we're gonna, the type of data we're gonna work with, how we're gonna randomize, and if you have restrictions or not, and the type of restriction. That was it, see you. I consider just runaway ones, remember now. So we can do a completely unrestricted randomization, or restrict the sums of the rows or the columns, or the number of the matrix field. If it's a binary matrix, the number of ones we have, or you can stratify these matrix like we did with the sampling periods. And we're going to go through some details on data type, general randomization processes, and restriction, and some combinations of those. The ones that I found more useful. So if we're going to use the data stream, the real data, groups into individuals, so that binary matrix. Usually we're going to use the swapping algorithm, pretty much same thing that we saw yesterday with the permutations. And we can restrict or not all of these things. If you're going to do, we can also use a probabilistic filling algorithm. The idea here is, instead of flipping things in your matrix, you create new ones, you just toss the ones in your matrix according to your based on your observed data. So we create new ones, and it might not restrict specifically like row sums and column totals and matrix field, but it will be pretty close. That's a different way of doing. If you're working with the relationships, so the association index, we might just shuffle them around the matrix, or you can use instead shuffle around the node attributes. So if you have males and females, you can shuffle this label among the nodes, or adults and juveniles, for example. And here, usually we want to compare means of the mean values within each of these categories. So we're going to shuffle them around as well, and usually we don't use any restriction. So data types, the 3 of them. First, what we call data stream is just the raw data that will generate the relationships between individuals. And as you know by now, is that famous binary matrix with individuals, A, B, C, D, and groups, 1, 2, and so on. So would be that binary matrix. So usually is our raw data, and usually it's better to randomize the data you collect instead of the relationships. But anyway, so we are working on either a binary matrix, or if you're dealing with interactions, it might be a quantitative matrix as well. If you have a number of touches or events that they do, fightings or whatever it is, you can use with quantitative. If you're working with community ecology and you have, I don't know, this is a plot here, and you have 10 individuals of the species A, 21 of the species 2, or 40, just to use the numbers there. It can be a quantitative one as well. So it's usually an asymmetric matrix. And in our case is this thing, individuals and groups. And yeah, what did you say? Good. The other type of data that can work is the relationships. In our case, usually it will be the association matrix, which is the same as the network. Remember that the network is nothing else than a plot of that triangular matrix. And usually we move from here to here using one type of association index, but it could be done in different ways. So in this case, in our case, we're shuffling then the values inside of the association matrix. Or if you represent this as an edge list, you will have A and B, A and C, and so on. And here the values, 0.9, and then you shuffle these values around. So it's pretty much same thing. So we have the square matrix. It could be binary if your network is binary, or quantitative if you have an index. Again, if you're working with interactions, it could be the number of times. It could be the number of times an individual, I don't know, high fives the other. That would be pretty cool. High five network. And usually we're talking about a weighted association matrix. Could be counts of behavior as well. And the other type of data we can work with is node attributes. So in this case, now we have a radian metric here. It could be, I don't know, a node degree, or essentially any metric you can have for each individual. And if they're from different classes, say sex or age or color or size, whatever it is. So we're gonna shuffle the class, these labels among individuals. So we're going to shuffle, we work with the node attributes, so pretty much the same as the supplemental data we put in SOCPROC, and could be social units or even modules that they are part of. If you figure out they have these modules and you find the membership for each social module, for example, we can shuffle them around. And here we are interested in the difference between the classes. So usually we are comparing the mean values within these two classes. Any questions on data type? No? Good? Yes?
So you were saying about shuffling the modules around. Would that take care of, so a lot of the metrics are quite dependent on the size of the network.
Yes.
With
Let me see. Maybe I'll take that back. Don't shuffle the models, models around. But if you have a different way of defining a social unit, now using modularity for, I don't know, let me see, it could be a certain number of years that individuals were consistently seen together. and then yeah, that would be a better way of doing it. Because you're right, the module membership is actually dependent on the network structure, so it wouldn't make much sense actually. I guess.
Good. No, I was more worried about the effect of the number of individuals in
Yes.
each group.
In each module.
So, yeah. So I mean that's one of the reasons you can't, besides them being non-independent, one of the reasons you can't compare metrics for different networks.
Yes.
So would it be okay to permute them like this and then compare your observed value to an expected value? Well, it doesn't make much sense anyway. Yeah.
Yeah. I think I'll take that part back. Forget about it.
No, that's cool. Yeah.
So, let me see. The algorithms, so this is very similar, if not the same as the permutation we seen yesterday. So there's the swap algorithm. Essentially is that finding those checkerboards and flipping them around the way we've seen already. And there, all of those improvements, increasing the number of flips to make your null matrices last non-independent. And so there's variations of these algorithms that we're going to see in the vegan package, but the idea is the same. And here we keep those restrictions of row sums and column sums. So yeah, we can also work. That's the same as permutation and Monte Carlo. The basic idea is just shuffling your matrix. We can use the same idea to shuffle the classes among nodes. And the third way of doing is a little bit different now, and it's based on a probability matrix. So we first create from our observed data, we create another matrix with probabilities for each cell, and then it's an empty matrix. We're gonna fill this matrices, just tossing around the number of observed ones we have, and they will fall into this other empty matrix according to the different probabilities we have. Let me try to explain that in a different way. So we're gonna fill in new empty matrices according to the observed probability. How are we gonna calculate this observed probability? It's
a probability of what?
Of filling the new. We have to create new matrices, right?
Okay.
So, for example, here we have 13 ones, 13 presences.
Yeah.
We want to create different ones here. Instead of shuffling, we're going to take this 13 off and then throw them again in a new matrix. And if it's completely random, they could, fill any cell here. But we want a little bit of restriction when creating this matrix. So we're going to create probabilities of filling these new cells here usually based on row, the sums of the columns and sums of the rows, sums of the rows, the sums of the columns. So at the end, you're not gonna restrict the same. You're not gonna have 3 here all the time, 2 here all the time. It might vary a little bit, but it will be closer to 3 than to 17, for example. It would be similar to this.
But there'll always be 13.
Yes. So you're gonna restrict the number of observations you have.
That's probably a pretty good algorithm because it takes the best of structure and adds some randomness.
Yes. You allow, for example, this guy we're seeing 4 times, they might have seen 5 or 6, a little bit around. Yes.
Yeah.
So
And
it's
when
not-
you permute, most likely they tend to be 4
Yes.
again.
very likely to be 4. If you permute,
If
with
you do the mean of all the permutation, they tend to
yes,
be.
it would be around this. That's the idea. I really like this approach actually.
Yeah, exactly.
So to create that proportion here, then I'll show you later how you can create this. At least, well, there's several ways. I'll show you 2 ways of creating, but it's basically just a proportion of these things divided by this. I'll show you in a minute. So, okay, so seeing the 3 data types, the 3 ways of shuffling the data, and now just remind you the restrictions. So the more restrictions we have, more statistical power. So we can start with restricting anything, just shuffling things around, including not even the number of observations you have. Yes.
This might be a really dumb question, but why would increasing the number of restrictions increase the statistical power?
Because then you're going to create matrices that are more similar to the one you observed. So if there's really a structure here, you're not comparing to the completely randomness. So your node distribution will be closer to the one you observed. So if there is a pattern and it's different, then you have. Remember what the statistical power is? It's 1 minus.
It's going to be easier to spot the
Yes.
the difference.
Yes. So if you compare with the completely randomness, you can have like all sorts of values here. And if you're gonna have all types of variation there. If you have a restrict permutation, you're not gonna have that much of a variation around it.
Basically, what you observe is caused by structure in your data other than real relationships. So by restricting your random data set, you're partitioning out any common underlying structure, group size, and your sampling kind of design. So maybe that's why power goes up.
Yeah, if you compare it with something that is, is completely different already, like a matrix with 3 zeros here, then chances are you're going to reject your null hypothesis. What you observed is it's more likely to be different than the totally randomness. And the more you make it similar to your original data, then if you reject that, then there's probably a structure there.
I think it isn't more. You're gonna have more chance to make the 2 type of error
Yes.
rather than reject, because the rejected null hypothesis could be fine.
Yes.
It's just that you have a higher chance. If you have a completely random, you have a higher chance to reject the null hypothesis on is true,
Yes.
or the other way around.
That's
So
right.
that's where the statistical power is like.
Yes. Yeah.
Right?
So the types of restriction we can have is known, or group size, the sum of the columns, the rows, right? Capture frequency, so the column totals. The matrix field, the number of observations or interactions you have. The number of individuals and the number of groups, in stratifying them like we did with the sampling periods to control for demographic effects. And in this case, you could do not only by periods of time, but by places, for example, as you mentioned. We can have 2 different areas that they might have, chance to move from one area or the other, but you kind of know there's this geographical segregation. You can include that as well. So yeah, just remember, that's the stratification. So you're going to restrict into blocks of your data. Could be space or time. The idea is to mostly controlling for demographic effects, for allowing the individuals that never be in the population at the same time, they're not, then in their permutations they're not going to be there. And yeah, so the way to fix this problem is splitting the matrix into blocks of time. Okay, so I'll give you some examples of how this works. You know this already, probably. So we're gonna, this works exactly the same as the permutations we were seeing yesterday. So we're gonna constrain row sums, which is group size in our case, column sums, which capture frequency. We have two different periods of time here, individuals in the column, and the columns, groups in the rows, and the total interaction. So it's a pretty constrained model. We go there and look for those submatrix, flips them around, do more or less 10,000 flips per interaction, calculate. From this, we calculated association matrix again. From this association matrix, we essentially would plot our network here. And then you calculate whatever you want, clustering coefficient, modularity, whatever you want, and save. Then you do save that value. Say you have a key value of 0.03. Then you go back there, shuffle again, 1,000 times, calculate this again, plot your matrix, calculate modularity, and save. Now we have modularity 0.02. And then keep doing this 1,000 times at least. Then you have all of your key values here. And then from here you calculate your coefficient, confidence intervals, and then compare your observed metrics. So basically what you have to choose is what you're testing here. We have done this yesterday for the mean values, for the CV of the association matrix. Now we're going to do the same for any network metric we have. Same idea. The shuffling thing. So if you're working on the edge list now, we have their individual, and the weight of interaction. So we can either shuffle the weights around them, which is same thing as shuffling your association matrix, right? It's just two different ways of looking. Or you could shuffle the nodes instead. Same idea. And then shuffle once, calculate modularity or clustering coefficient, save, and plot there in your distribution. Then shuffle again, calculate again, and do it again. And do this 20,000 times or 1,000 times. You have your distribution, and then you compare your observed value with the 95 confidence interval. And
sorry, you put 20,000 because it needs more iteration to have higher statistical power than the shuffling, or?
yes, I mean 1,000 is good enough.
No, because you put 20,000 there.
Yes.
It's just a number? Ah, okay. So it's not that it needs more than the previous one.
No, you can do, you can do 1,000 times.
Ah, okay.
It's usually, the more you do, more you're gonna have more definition in your neural distribution. If you shuffle 3 times, then it's usually 1,000 is good. And finally, an example of the probabilistic one. So we start with the same data, same idea. Now we have some restrictions, but we're not gonna keep exactly the same. We'll be based on that one. So from here we move to create our probabilistic matrix. So let's see if we can do this. We might want to turn off the camera. So this is one way of doing. We can be based on group size. So let's see 3 here. So let's see if we can calculate this one. So we have PI divided by C plus PJ divided by R, and all of this divided by Q. So PI is the row sum, would be 3. C, if I remember well, where is C now? It's number of individuals, I guess.
5.
4.
4, sorry.
4. Plus PJ is 4 divided by 5. And this divided by 2. Actually, it's 3, 4, 5. It's 0.07. No, I don't know. I'm going to check.
20, 15,
I'm just-
15 plus
I'm lazy now.
16 is 30,
Anyone that's-
30. 31 over 20 divided by 2.
I'll be back in a minute. Let's see.
31 over 40.
31 over 40. Please be that. Yeah, no, it's not. Let me see. Let me see. 3 divided by 3 will make 4. Okay. And then 4 will make 5. Okay. That would never be. That's impossible. I got something wrong. Definitely turn that thing off. Yeah. Come on, that's not. Sorry about that. Let me double check what we've done here. Correct. Take that on camera.
Yeah.
But I'm wrong. So there's 2 ways we can do it. And for this example, I use this way, right? According to him. The other way would be using this other probability here. So
Unless divided by 2 is on the exponent.
no, I think that's the way it is actually.
Good.
The formula is right actually. I'll show
No.
yeah.
How can the other one be right?
So then we got the raw information. So we have, yeah, that's the same
Yeah,
formula.
that's correct.
So PI is the row sums. Row sum. PJ is the column sums. This is the
Columns.
number of columns. And this is
Number
the
of
number
rows.
of rows. So it would be group size, right? Would be capturability, would be number of individuals, and here would be number of groups divided by 2. So yeah, no. So okay, it is. So there's 2 ways we can do it. One is this way, we just multiply the PI, which is the row sums, for the capture frequency and divide it by 13. Yeah, 13. How do you say that again? 13 squared. Sometimes to the power of 2. I prefer that one. Or you can use another way. It doesn't really matter. What we will create here, now to bring back the idea, you have these matrix with different probabilities in each cell. So we're gonna toss this 13 observations here, and they will, in this case, be more likely to fall here or here and last on this place. So you have this probability of keeping the same number, group number or capture frequency. right? It won't be exactly the same, but if you do enough times, then you're gonna have a reasonable range of change.
Is this probabilistic fill-in also available for what we did the other days in terms of the shuffling?
For the
Permutation.
Not really. I mean, not in Socrates, but
Yeah.
you could do this to test that way if you want. I have done that before, and at that time it was like pages of code, but because I'm terrible at coding, but I'm sure you can do that in a few lines. And if you're interested, I'm more than happy to put that together because it's one way of doing it. Actually, we're gonna do this soon. We're gonna do this for modularity, but then we could calculate the mean if you want, and then that's essentially the same. Just a different way of doing this. In this way, you avoid those problems of no independence because of the flipping, for example. I think it was at that time that they published, I think in 2009, they published a paper saying, oh, this method of flipping is flawed because your matrices are dependent one of each other. And that was a way of getting around. But now they increased the number of flips, so everything's fine. Everybody's happy. That's how it should be. So and then from here on is the same. The only change in the step is, instead of preserving this exactly the way it is, we're going to use this will be based on that. That's a model. I think the guy who created this model, I don't know if he created, but anyway, it's famous in a paper in 2013 with networks of seed dispersion. So they have species and like animal species here, think birds, and fruit species there. Right, so I'll just summarize this and then we start doing. So we can either work on the raw data, group by individual, and if you're doing that, we can swap things, shuffle things, or use this probabilistic. We can use no restrictions or all types of restrictions we have. Group size, capturability, matrix fill, network size, demographic facts. So if you work with the raw data, you can do anything. And it's available in SockRock, in the vegan package in R, or the, I forgot, it's not missing an E here, or even in modular, if you're working with modularity. If you're shuffling or randomizing relationships, you will work on either association matrix or network AgileList, and basically we're gonna shuffle them, either the nodes or the individual, the weights. We will preserve the link weight distribution, the number of individuals, network size, the number of links, connectors, and we can add strata if you want. And we can do that in R easily or in SockRock. And if you're working with the attributes, then we're gonna work with AgileList and the categorical variables, sex, age, so on. You're gonna shuffle them, and this is, you can do that in SockRock if you want, but more easily in R. Good. Now, hopefully all of this will make more sense in R, and hopefully that thing will make sense now, because if not, I have a couple papers to throw in the garbage. Okay, so there's two scripts for you. The new models, this one is a long one. We start with a step-by-step randomization. Then we run one of the new models step by step to create the null distribution step by step. And then there's 8 new models for you to play around with. And at each step we calculate the new matrix and take a look how it looks like, if it preserves this, preserves that. And then if you want that, again, extra for the super keen people, we can run the same test that we've done in SockRock yesterday in R. So with this package here, you can do that. pretty much same thing. If you want to do by hand or step by step, there's an option there. So let's start playing with this one. And that's it. Any questions or tomatoes to throw? That. No, sorry about that. Okay.
Three.
Okay. Just gonna run the first part of it with you, just to show step by step how the shuffling thing works, and then how one new model works, and then you can go ahead and try all the, I think, 8 possibilities we have. Just functions. So you need to upload this script here called functions.r, where all the new models are. Essentially recreates all of those new models into functions, but they're all, just using, pretty much all of them using functions from the vegan package, just organized into another little function if you want to use that specifically, instead of figuring out the combination of arguments that you need to run, say a swapping algorithm that constrains this, don't constrain that. So there's all the options there in little functions. In the probabilistic field one, I borrowed from a friend of mine who developed that function, and it's here for you guys as well. So if you look at the function here, there'll be new model A to H, and the ones with Q in front of them you can use to quantitative matrices. So if you have counts instead of binary data, so it's the same idea, but for this is, so you go in the workshop material, there'll be software, and there's a R script called functions. So when you open that, you have all of this organized. There's a little help file here if you want to waste your Sunday, go ahead and do it. And feel free to change the code if you want to. So yeah, so all of these functions here, they're all based on the perma full function of the vegan, but just organized in a way that one will fix the row sums, the other will fix both, and so on. So let me start with you doing the basic one, and then you guys go ahead and play. Just including the data here. So we have three types of data to play with. One is the association matrix. The other is the edge list of this association matrix. The other one is the iGraph version of the same association matrix. Sorry, there was 4. So, and the other one is a matrix of interactions. This is a fake one with quantitative values if you want to play with that. So instead of, it's a square matrix, but this guy, I don't know, high fives the other one twice, and so on. So it's a matrix of high fives. That's going to be it now. So to show you how the shuffling thing works, they're based on these the error function called sample. So what we have is, if we start with a whatever vector is, just creating a random vector over there. So I just create a random vector from the uniform distribution. So we have these values, right? So we can just sample it, essentially just shuffle it. So what the function, we have the same values but in different orders. That's the simplest way of doing it. So that was our original one, and our shuffled one would be, random orders. If you do that a couple times, you're gonna have different combinations of these vectors. Okay? That's the basic idea before. You could do it if you want later. You could just, sample this vector here. Instead of giving me all of the 10 values, just give me 3, or just give me 5. Give me a high 5. 3 of them. It will sample from your original vector without replacement, or you can, if you want to replace, you can sample with replacement, and sometimes you're gonna get the same. See? Yeah, sometimes you get the same value. So that's more or less, that's the function we're gonna use to shuffle our matrix. Is that clear? Easy.
What's the difference between the one where you replace and the one where you don't?
So imagine you have a bag of values here, 1, 2, 10, 25. If I sample, I'll just pick this one without replacement. I take it, now I'll put 25 here, and it's not there anymore. The next one I'll pick 10, and it's not there
so
anymore.
you can get like 2 of the same numbers.
Yes.
Okay.
Replacement of it.
Okay.
Yep.
Seems-
It's going to be useful tomorrow for bootstrap and jackknife. So one you do with replacement and the other you do without replacement. So let's walk through a simple new model for modularity. We're going to do step by step, and then you take a look in the other options. This is the simpler one. We're just going to shuffle the weights in the network. So we have this network here, or not. We have this network here, and this is the observed one. We're going to calculate modularity for it, and then we're going to shuffle this link with the other one. Just shuffle it around, calculate 1,000 times, and see how different that is, if it's different. So first thing we do is calculate the original, the empirical modularity value using, for example, the walk trap function. And the modularity is saved here, now observed, and it's about 6%, not much. These are the guys in different modules. We have 2 groups of them. Okay, so what we're going to do is take this matrix or edge list and shuffle this around. So essentially we're going to keep these pairs here and then use the sample function to randomize this. It's very simple. So this is the vector we're going to sample. All the weights, all of these weights displayed here are here. Is everybody following? Okay. Good. Let me know if I'm too slow or too fast. So we're going to sample, so just shuffle that around. So we have the same values but in different positions. Okay? Good. Now what we have to do is we sample and then save in this random object. So we have our original, we have the original edge list. Never know, I'm just thinking like this. I hate the ages, man. Right. Anyway, I'll move for this. So we have 1, 2, 3, 4. So we have the original one, we make a copy of it, shuffle this. So say 0, 5, 9, 3. This is one iteration for here to here. So we calculate Q for this, calculate Q for this one will be our Q random into this 1,000 times. So we apply the sample function to this column here, sample, and create a loop to do this 1,000 times, and every time save the Q dot. Ready? Good. So let's just compare. This is our observed one. And this is our random one. It's going to be hard. Just look at the last two pairs, for example. The original one is 12 and 14. They have 0.4. The other one is 0.18. When we randomize, now they have different values. Good. Okay. Now we calculate. We transform this random copy into a edge list, into a graph, iGraph object. Put the weights on it, and then sample. Actually, I'm gonna sample right now. Sample the weights around, and calculate the modularity. So that's our modularity here. So now we have for this random copy here is 0.046. We still have two groups, different individuals. Then the observed one was 0.06, and now 0.046. Now we do this 1,000 times. So, okay, that's the original one, and that's the random one. Better? Cool?
And obviously the ones that you get and the one that we get is different between the two.
Yes. Yes. Now we want to see how much this can vary. Will vary. Maybe you can get, I don't know, 0.9 from that. Even though we're gonna do this enough times, maybe 1,000. Just like this. Now we're gonna repeat this in a loop from 1 to 1,000. To do that, we need to create an empty vector to save each Q value, right? So now we have an empty vector here that we'll save. So everything that I've just done, we're going to repeat inside of the for loop here. You guys are familiar with for loops? Not fruit loops. Those are pretty good. For loops. Nope. Not familiar? Not familiar? So what it does is, it's a way of doing a loop, repeating a chunk of code. So it works like this. You have a for is a function. It goes from that value, could be I, A, whatever you want. And this value will be within an interval. There, say 1, 2, 10. So you collect the 10. And then you will open these curly brackets. Is that how it works? And then you close it here. some reason I can only make this one side close every day. So whatever chunk of code you have inside here, it will repeat within this interval, 1 to 10. Okay, so
So in the real scenario, it would be 1 to 20,000 then?
yes, or 1 to 1,000. Here my iter object is
Oh,
1,000.
the 1,000 that we said.
So everything that I've done once, I'll put inside and then run this code. It will, every time he runs, he updates the value of I. So it starts with I equals 1, and then he runs here, for example. What we're gonna do there is we have rand mode I, and then you do whatever you want here. So in the first round of the loop, this I is equal 1, right? So everything inside of this chunk that is equal, as I would be equal 1. So the first position of this vector will receive whatever I put over here. And then when it reaches here, it goes back up. Now I equals 2. So everything that has I inside of my chunk will be 2 now. So the second position of my vector will be 2. So we'll save here in the second position. Comes here now with I equals 3 and so on until we reach 10. When it reaches 10 in this case, it exits the loop. So let me show what's inside of my Fruit Loops here. What?
Fruit Loops.
Fruit. It's gonna be.
Yeah, you think.
So iter in my case is 1,000. So we run this chunk here for 1,000 times. So let's do it by hand then. So let's see, I in this case is 2. Let's start. I equals 1, okay? So I equals 1. Here. So I equals 1. So first thing it does, it makes a copy of the original address and copies into this random auxiliary random, whatever you want to call it. So it makes this copy, makes a copy of it, transform this into a igraph format. Now we permutate their links. So see, this is our copy of the original ones. The weights they have right now, it's exactly as the original one, in that order. Okay, saved here. I'm gonna sample this. So I'm gonna sample this object here and then save on itself. Okay. Now I'm gonna calculate the modularity for this new object which has sampled it. Follow? Okay. Okay. So that's what it is now. We have all this information, but everything that I need is just the Q value, which is we can extract by here. So that's what we want. Now we're gonna save this value in the position 1 of that vector. So this vector is empty right now. So if you run this once, it will have 1 value. Now it reaches the curly bracket, and now bracket, and now I is 2. So we'll do it again and fill the second position. Do it again and again and again until 1,000. So to start with, it's 0, and then if you run the whole thing, take a few seconds. Now, what we have here is 1,000 value, no Q values. So we have our distribution now. Beautiful, isn't it? Let's take a look at it. So, and model. first. Let's plot it to see what's going on. So I'm just plotting these factors that I just showed you. So this is how it looks like. So we have shuffling all the links around and calculating key values for each time we have this distribution. So it's not, we're gonna compare now, we're gonna put our observed value somewhere here. I think it was 6, right? So it's pretty much here. So that means very likely it's not significant. So we can calculate the confidence intervals here. So I'm using the function quantile just to take, it's alpha of 5%, so two-tailed test, 2.5 that way, 9.75 this way, and this is the confidence interval. So just here. So we have a Q value of, I think it was 6, and our 95% confidence interval goes from 0.01 to 0.11. So it's within the no expectation. So I'd say it's not significant. Go back to the future. Abandon your project. No. This is just another way of presenting your data. There it is. Or we can.
So basically, here you're saying that it's just, it could have happened by chance.
That's it.
Well, it did happen by chance,
Yeah.
especially considering.
There is still
Yeah. Yeah. No, in this case, it happened by chance because it's fake data.
Ah, okay, okay.
But yeah, but that's
Okay,
it.
say that was a real data. It could have happened by chance, which that doesn't mean. What does it basically? What does it mean that what you thinking you're seeing?
It's
It's
very
not
likely to be real.
Yes.
Yeah.
So it means that
So
network.
whatever information you try to come up from that graph, that your exploration is not. You can't defend it mentally.
Yes. So that's one very good. So what is in this case we're testing for modularity, right?
Mm-hmm.
This is a terrible way of making that. Yeah. So if you're saying that there's modules here, this test is showing the structure you're seeing is likely to emerge just by chance. Now, if you have, for example, 60% here, and by chance you can only get these values here, so this is a highly significant one. What you're saying is the observed modularity is way higher than you would expect by chance. And in this case, it's more or less what you would expect by chance.
So you can publish your paper.
Well, you can still publish, but good luck with your arguments. No, I mean, depending on the question, not being modular might be amazing.
Yeah.
For example, for
Ah,
the
yeah,
orchids, for
Yeah,
example,
it would be
we know that they are
very amazing.
structured in multi-levels and they have these kind of social units, and if you show that they
Yeah,
don't,
they're-
that's a good. So it depends on what
Yeah, sure.
always the case. So don't cry for that. Yeah, it depends on the question. So that's one way of doing step by step. Now from the rest of the script, well, I'm just plotting this in a nicer way. So this is our distribution. This is the observed one right in the middle. This is the confidence intervals. So it's right in the middle. So too bad in this case. Now, the next section contains 8 new models. So the idea is the same, but just the way you randomize your data is different. And you want to think about which one is best for your specific question. But if you want to go ahead and play with this, it's pretty much self-explanatory, step by step. So I tried to make this way so even if you don't have time to go through here, but you want to use later on in your lives, in a Saturday afternoon, because on Sunday you're doing the other type of permutation. So you can go and take a look what type of input you have, what is it doing, if there's any restrictions, and what you would get as an output. And yeah, there will be, I think, 8 of those with relationships if you want. And then at the very end, this template here, it's pretty much, so all of this exercise above would be just shuffling the data, right? But then if you want to test a different metric, non-modularity, you want to test, I don't know, connectors, whatever you want. So here's at the end, there's a template code for this. So you just change at the beginning your data, the number of interactions, the new model you have, and you change at the beginning and run the rest, it will create for you. So more or less, you need to adjust a little bit. Don't take it too seriously because I'm probably drunk on this.
Sorry, the last one is if you want to run instead of modularity or another
Yes.
parameter.
Yeah. So it's just in this template. I think this.
Can't you just change them?
No. Let me see. So it would be.
No, I understand the concept.
Yes.
But this whole code here, you don't just change the.
Yeah, you have to adapt. I mean, it's adapted for. In this case, I'm using this metric, but if you want to calculate the connectance, for example.
That's where you change it. Okay.
Yeah,
okay,
then you
okay.
can put the formula here, and then go step by step and see if it makes sense.
Okay.
But
And the probabilistic one, you have it there as well?
yes, we can go through the probabilistic one. I think it's notations. Notation constructor.
214?
I think it's
214, line 214?
204.
At least I remember mine. No. Yeah.
274. Yeah, there's 2 probabilistic ones. It's what I called here nu A and nu B. So one of them will create one. So the new model A will use this function here. This one will use this formula here, the other will use this one. But they should be pretty much the same. So let me see, 3:30. So what are you guys up to?
A beer.
Huh?
A beer.
A big nature. For sure.
I see you.
Stop it, it's okay. Hello. Gosh.
So if you want to run by yourself, so you walk around, see if you have any questions. Of course, if you want to, I think we're past our time, so if you want to leave as well, feel free. Correct.